placement test prep. And let's start with 2a. If we're going to solve this equation for x, the first thing we want to look at is, do we have different degrees of x? And if you have x's with different exponents, then you're always going to set the equation equal to 0. Okay, so we could say these variables have more than 1 degree. This has an exponent of 2, has an exponent of 1. We got to set it equal to 0. So let's add 15 to both sides. And then you can subtract 2x from both sides. If you do that all in one step, I'm okay with that as long as you are accurate. And then to solve for x now, we're going to use zero product property. And that says that if you can set the factors equal to 0, then you'll find the things that make this equal 0, because this one is pretty straightforward. I don't really need big X. Feel free to use big X if you want. 16 can only be 16 times 1, 8 times 2, or 4 times 4. Well, the only combination that will get you 10 is an 8 and a 2. And they both have to be negative because they multiply to be a positive. Then you set each equal to 0. You get x equals 8, x equals 2. And those are the solutions to the equation above. Okay. Now, for right now, when the problem starts, I only have 1 degree on my x, and all my x's are inside these parentheses. That means I'm going to solve by isolating x, and I'm going to use reverse PEMDAS. So what I want to do is get all my x's on the same side. So that 4 is added. So I'm going to get rid of that first because of the add subtract using inverse operations. 3. So I divide both sides by 3. Biggest mistake people do here is they try to cube root first, but this comes before exponents. So now I have x minus 1, parentheses cubed, equals negative. It says evaluate the exponent, or get rid of the exponent, and we want to use inverse operations there. So a cube root cancels out a cube, and then I'll have a cube root of negative 10 over here. I don't have to do plus and minus on a cube root. I have x minus 1 equals cube root of negative 10. The parentheses are now gone, and so now I kind of start over, and I have to add 1 to both sides. All right. Once again, we only have 1 exponent. That doesn't say D and E. That says 1 exponent. And so we're going to isolate the x. So again, just use your inverse operation. And the real reason this is here is to show you kind of this last step. So I get x squared equals 20 over 9. I'm going to square root both sides. And when I square root a variable, the other side always gets the plus and minus. Now let's start to simplify this. That's the same thing as square root of 20 over square root of 9, which is the same thing as 3 on the bottom, right? Because the square root of 9 is 3. And then 20 is root 4 times root 5. So the square root of 4 becomes a 2, root 5. And that's it. By the way, this is called simplifying square roots. If you forgot how to do that, you can Google simplifying square roots. And moving on here. Again, we just need to isolate x. So there's nothing added or subtracted. So I'm going to divide by 2. And you can't separate like sine from x. That's all stuck together. So what we usually do when we get to this point is we just use our knowledge. First of all, they're telling us don't worry about anything except for answers that are between 0 and 2 pi. Because since sine is periodic, it goes on forever. They're like, just basically worry about the unit circle. So for what values of x, for what radian values, if you plug them into sine, would you get 1/2? Well, that would happen when x is pi over 6, right? Because sine of pi over 6 is 1/2. And then let's ask ourselves about the other ones. Because any pi over 6 for sine is going to have a 1/2. You just have to decide if the 1/2 is positive or negative. So pi over 6 is quadrant 1, that's positive. This one is quadrant 2, that's positive for sine. Quadrant 3 is negative for sine, so it would be negative 1/2. And quadrant 4 is negative 1/2 for sine. So what that tells me is that my answers are going to be pi over 6 and 5 pi over 6. 3a. So when you have a rational exponent, the first number is the top number is the power, and the bottom number is the root. So you can remember power up, root down. So here's the root and the power. Usually if you have these and it's involving integers, usually there's some sort of way you can find the root so that you don't have to multiply 81 times 81 times 81. And if you take 81 and you think about it, it's 9 times 9. And that breaks down to 3 times 3 times 3. So 3 to the 4th power equals 81. So that means if I take the 4th root of 81, I would get 3. And then that's raised to the power of 3. 3 times 3 is 9 times 3 is 27. Okay, you could do it this way and do 81 times 81 times 81 and then take the 4th root. But that would be nearly impossible without a calculator. So I don't recommend that method here. This one, a power of negative 1 literally means take the reciprocal. So if you consider this as 5 over 1 to the power of negative 1, a negative 1 exponent means take the reciprocal. Okay, so some people would teach this as 6 to the power of 2 to the power of negative 1. Do you see how that would be 6 to negative 2? So it'd be 1 over 6 squared, which is 36. I think most people skip this step, and they just go kind of right to here. Okay, 5a, we're supposed to simplify. Now, if you have a rational expression, that is an expression that's a fraction with variables in the top and the bottom, I want you to simplify. Usually, you should be able to factor and cancel. So hopefully you know off your head that the factorization of x squared minus 9 is x plus 3x minus 3. Here on the bottom, you're welcome to do big X, but also you should be getting some facility with doing this in your head. There must be a plus and a minus to get a negative 12. 12 can only be 12 times 1, 6 times 2, or 3 times 4. And so to get 1x, it would have to be the 3 and the 4. The 4 is going to be positive to make the 1x positive. Again, use big X if you'd like. Then those cancel. And I have x plus 3 over x plus 4. However, these expressions are not quite exactly the same. This expression has an undefined point at x equals negative 4 and x equals 3, right? Because of these factors, right? This only has an undefined point at x equals negative 4. So we have to say that, hey, this is not the same as this when x equals 3. Because when x equals 3 here, you have 6 over 7. When x equals 3 here, you have undefined. So this is what we call an excluded value. Don't worry too much about that for the placement test. I'm mostly seeing if you can factor and cancel. Here, there's no binomial on the bottom, so you don't have to spend your time trying to factor that. I think what I'm looking at is, can I factor out a 2? So in the numerator, there is a greatest common factor between each of these terms, and it's 2. So that would get me 4x squared plus 5. And so then these 2's cancel. And then it's important to know that you cannot cancel this x, because you may not cancel individual terms or parts of individual terms from an added or subtracted expression. Okay, if you have a subtraction with addition and if you have an expression with addition and subtraction, you cannot cancel from within it unless you are able to factor something out completely. Okay, because this 2 divides literally into every term, I was able to cancel it. But usually we say you have to factor out and then cancel. If you canceled x's here, that you would have it wrong. And then some people might say, well, aren't I supposed to factor this? I mean, not really. There's nothing for it to simplify with, and it doesn't factor anyway. Okay, C, look up synthetic division and divide top by bottom. Okay, make sure you look that up and get your answer there. So let's take a look at number 8, piecewise functions. Look, this is going to be really important for calculus, and I feel like you've learned piecewise functions in all 3 grades now. And so here's kind of your last lesson in piecewise functions. This function is made up of 3 parts. A parabola, which is x squared minus 3, and a linear equation, 2x plus 5, and another parabola, negative x squared minus 3. This is a really bad drawing of it. But the thing with this equation is, hey, look, this x squared minus 3, literally only use that when x is less than negative 2. So I don't need this whole part of that parabola. Okay? 2x plus 5, hey, only use this between 2. This doesn't quite line up, but we're close. Only use this one between negative 2 and positive 2. So here's positive 2 about here. Okay? And then only use this one when x is bigger than 2. So I don't need like any of this. So at a rough sketch, here's what my function is going to look like. Okay? Part of a parabola when x is less than 2. A linear between negative 2 and 2. And then part of a reflected parabola when x is greater than 2. Now, this sketch, it's not accurate enough to put on a real graph. So I have to get some real points on this. So since this one is for x's less than negative 2, why don't I just do like negative 2, negative 3, negative 4. I am going to go ahead and include the negative 2 right here because I want to go all the way up to that and put an open circle there. So if I put a negative 4 in here, I get 16 minus 3 is 13. Hopefully you're doing this on your own. 1. Is that right? That can't be right. 16 minus 3 is 13. 9 minus 3 is 6. There we go. And 1. So here I have negative 2, comma 1, and that's an open circle. And then I have negative 3, comma 6, negative 4, comma way, way up there. So I'm going to go ahead and draw that. And that goes to infinity. Okay. And then for my linear here, 2x plus 5, right? And that starts at negative 2. So if I plug in negative 2, I have negative 4 plus 5 is positive 1. Hey, look, that puts me right here. So that actually means that I can color in this circle because there is a point 2, 1. Now, it's linear, so why don't I just go up 2 over 1, up 2 over 1, up 2 over 1, 2 over 1. Right? And I mean, I can fill that in there, but I mean, really, I'm just going to use slope because I know how to do it. Oops, I should have stopped right there. And let's just double check at this 2. That's going to be 2 comma 9. And 1, 2, 3, 5, 7, 8, 9. Hey, got it. Okay. Inverted parabola here. We're going to have an open circle when x is 2. Remember that negative x squared is negative 1 times 2 to the power of 2 minus 3. You do your squaring first. So that's negative 4 minus 3. So that's negative 7. So at 2, negative 7, 1, 2, 3, 4, 5, 6, 7, we're going to have an open circle. And then this would be negative 9 minus 3 is negative 12. And negative 17, I think. Wait, negative 19. Okay, 7, 8, 9, 10, 11, 12-ish. And then one right on here. So, all right, so there's my function. Number 9. This page You have to memorize this stuff. I mean, you should have already memorized it. But for my placement test, like memorize this. This is all like important stuff that is definitely a need to know for AP Calc. Vertical asymptote. When you're looking at a rational expression, a vertical asymptote is when you have a non-zero number over 0. Okay, in other words, if your denominator equals 0, that's going to be a vertical asymptote. So let's set our denominator equal to 0 and solve for x. So you got to know if you're asked for vertical asymptotes, you take that denominator and set it equal to 0, because you're basically looking for points where this is undefined. Special big X is the way to go here. Negative 42 on top, 19 on the bottom. Hopefully you're going to take a second and figure this out, because on my placement test, you're not going to have a calculator. And you would figure out this 21 and negative 2. And then we're factoring by grouping here, plus 21x minus 2x. I got that from here. 7 equals 0. So all this did was split my 19 and made it 21x minus 2x. Factor by grouping, I look at the first half here. The GCF is 3x, and I get 2x plus 7. Bring down this negative. Nothing in common here, so I put a 1. And that flips that sign. And then factor out my 2x plus 7. And I'm going to pause for a minute before I finish solving this. If our original equation had been written like this, then it would have been really easy to find the two places where this is undefined, which is going to be our vertical asymptotes. So here, 3x minus 1 equals 0. That means x equals 1/3. And 2x plus 7 equals 0. That ends up being x equals negative 7 over 2. So our answer is here. So those points are both undefined. And on the graph, we would see like that dotted line in the graph going up or down as it approaches these. Okay, memorize what to do when it asks you for a vertical asymptote. If you're asked to find zeros or x-intercepts, remember the ordered pair for an x-intercept is a number, comma, 0. So you set your equation equal to 0. That's like saying make the y 0. And so what we would do here is we would say 6x squared minus 24 over 6x squared plus 19x minus 7 equals 0. In a fraction, if the numerator is equal to 0 and the denominator is some sort of number, that's what makes it equal 0. So basically, we're going to set the numerator equal to 0. Right? Because if the numerator is 0, then this fraction is 0. A couple ways you can do this, but let's just add 24 to both sides. 6x squared equals 24. That means x squared equals 4. Square root both sides with your plus and minus. And x equals plus and minus 2. Okay, so memorize this. If you have to find zeros or x-intercepts, you set the whole equation equal to 0. If you're dealing with a rational expression that is a fraction, then it really means you're setting the numerator equal to 0. Y-intercept. Set the x equal to 0. It's also the same as finding f of 0. Okay, so if you set all your x's equal to 0 here, what would you get? Negative 24 over negative 27. That's positive 24 over 27. 24 over 7. Horizontal asymptote. Okay, that's always going to be a y equals thing. And this is really the same as asking sort of for end behavior. So if you have the same degree on top and bottom, like your highest degree on top is x squared and your highest degree on the bottom is x squared, then you use the ratio of the coefficients. So if we look here, we have 6x squared on top, and we have x squared on top and x squared on the bottom. So there is going to be a horizontal asymptote, and it's going to be the leading coefficient divided by the leading coefficient. So in this case, as x approaches infinity, f of x is going to get closer and closer to 1. That means we have a horizontal asymptote at y equals 1. Okay, so the end behavior is as x approaches infinity, f of x approaches 1. They ask for horizontal asymptote, so it's at y equals 1. Okay, now in other scenarios, if you had a higher degree on top and a smaller degree on the bottom, so let's say you had 6x to the power of 9 and a lot of other stuff, and 12x to the power of 3, you have this bigger growth on top. This x to the 9th is going to make this get bigger and bigger and bigger and bigger. So that means as x approaches infinity, f of x also approaches infinity. And there's no horizontal asymptote if that happens. There just isn't one. And then if you have a smaller degree on top, like if you had 6x to the power of 3 on top, and you have, 6x to the power of 11 on the bottom with all this other junk, then what's going to happen is the top's going to grow, but the bottom's going to grow really, really fast. So that means as x goes to infinity, this fraction is getting smaller and smaller and smaller. It's approaching 0. And that's where your y-intercept is. You should review your end behavior and horizontal asymptotes. And again, easy to look up a video on horizontal asymptotes in rational expressions is how you would look that up. Okay, I'm going to pause this and actually I'm going to stop this.